each one of these categories across these different distances. But this is what makes us unique. We're the one-stop shop. We're the leader across the entire connectivity stack. And that brings us to the next major challenge facing the industry. So what you probably notice as I describe these different solutions in the last couple of slides is there's different solutions for different distances, and that some of those connections today are optical, and some of those connections today are electrical. And it's actually defined by distance. And so the connections on the left side of this chart are optical today. That means they use fiber optic cables to transmit light with complex electronics on either side of the cable to drive and modulate the laser that's transmitting that light. The connections on the right side of this are electrical, so they use copper cables or just copper traces that are printed on the circuit board, or even microscopic copper routing inside the package. So the common theme here is copper. And in the middle, you see the wall, the copper wall. And the wall is defined by the longest distance you can transmit a signal over copper. So before you have to move to an optical connection. So this is an important distinction because copper is simple and it's low cost, and as Jensen said, you want to use it for as long as you can. It's very practical. But optics is more complicated. It requires lasers, photonics, complex electronics. So it's a bigger lift, but it's going to be needed. And the copper wall, what I'm here to tell you today, is it's about to move. It's going to move again, and it's going to take over the rack itself. So this is creating an explosion in demand for the optical industry. And incredibly complex engineering challenges are coming and along the way. So why is this happening? So it's not just somebody's preference to go do this. This is physics. The distance a signal can travel over a copper cable is inversely proportional to the bandwidth. So every time you double the bandwidth, you have to cut the distance in half. Today, the highest speed production systems in the world run at 200 gigabits per second per lane, just to give you an example. So at that bandwidth, the cable length is limited to roughly 2.5 meters. Now, by comparison, systems running at 100 gig could use about 5-meter cables. And the height of the rack is about 2 meters. So once you account for all the routing inside the rack, 2.5 meters is right at the limit. So when we move to 400 gig, we can no longer fully connect the rack with copper. So the wall is moving, and it's moving now. And going forward, even the connections within the rack will become optical, and the whole industry knows this is coming. So we've been preparing for this moment, not just Marvell, but the industry. And you see this in Taiwan, by the way, in the supply chain and the ramp up that's happening. The ramifications for this are actually enormous because each time the wall moves one step to the right, the number of connections that you have goes up by at least an order of magnitude. So it's creating this explosion in demand, as I mentioned, and the optical supply chain needs to scale up massively and be ready. But we've seen this movie before, okay? I mean, 20 years ago, and I remember this, when state-of-the-art was 10 gigabits per second inside the data center. It was 10 gig. And we used copper cables all across the data center. Optics back then was reserved for just very, very long distances. It was essentially like a telecom technology, but when the wall moved, the optics industry actually rose to the challenge. And today, all the hyperscale data centers in the world, they're all optically connected. And as we saw in that transition, it did require new solutions. You couldn't use the same power-hungry kind of telecom approach, which is where PAM4 came in. It was optimized for power, density, and reach, and requirements specifically tuned to inside the data center. And Marvell was one of the key innovators there. So we're about to see the same wave of innovation needed as optics moves inside the rack. And that's with a technology called co-packaged optics, or CPO. You hear a lot about this now. I'm going to tell you more. CPO is a technology where we bring the optical connections all the way to the package itself, right next to the compute, either the custom compute or the switching silicon. And the fundamental challenge we're solving with CPO is density and power. Now remember, the number of connections inside the rack is like 10x the number of connections between the racks. So if we just try to use the same optical technology used across the racks in the data center, you wouldn't have enough power, you wouldn't have enough physical space, you cannot fit all these standard optical modules and cables as they are today. It just doesn't work, it's not possible. So the industry has been inventing this co-packaged optics concept, which brings the optical fiber right to the package, and it tightly couples the electronics that drive the signal over the fiber directly with the custom compute or switching silicon. So this is a massive change, and it's hard because you're combining some of the most advanced technologies in the chip industry, leading edge CMOS, silicon photonics, advanced packaging, optical interconnect, all manufactured in a small, tightly integrated system. So the complexity is very high, but it's the only way to continue scaling bandwidth and overcome this limitation that I talked about with copper, while reducing power at the same time. So this is where the industry is headed, and this is one of the reasons that Marvell has invested for more than a decade in silicon photonics, optical DSPs, all the analog broadband components around it, and all the advanced packaging you need to pull this off. It needs to all come together actually in CPO. So this isn't some futuristic thing, guys. Okay, it's happening now. And in fact, I brought a couple of Marvell examples with me today, so let's do a quick show and tell. Okay, so over here you have a traditional Ethernet switch. This is our 100T Teralink switch that we announced today, and you guys are the first to see it actually, everybody here in the room. You can see the switch in the middle of the board. Copper traces inside the PCB carry the signal to the front panel, which is here, and this is where all the optical modules plug in. Now, let's move over here. This is a CPO-based switch right here. Now, notice that there's still the switch silicon in the middle. That's right in the center of the die, of the package. In this case, this is our 51.2T switch, and all around the edges are 16 3.2T optical engines. So the 16 times 3.2, you get 51.2. So this is the fibers directly attached now to these engines. It's not to the front panel. So we've completely eliminated the copper traces on the PCB. Light comes directly out of the package. Okay, this is a very, very complex piece of engineering, and it was very cool to be able to show this off today. Okay, so co-packaged optics is here, and the industry is scaling up to meet the challenge. And as we've seen time and time again, every time we reach a physical barrier, we break through it with technology and innovation. In this case, by replacing copper with fiber, because unlike electrons traveling over copper wires, the distance that photons can carry a signal through glass is largely unrelated to the bandwidth. So as AI infrastructure demands even higher transmission speeds and needs to scale to larger and more complex systems, spanning millions of processors woven together now, not thousands or hundreds, optical connectivity will increasingly become the de facto solution. So the real question becomes, what does it take to deliver optics across the full AI infrastructure stack? What's it going to take? Well, it starts with recognizing there is no single technology for the entire data center. It's not how this works. There's no one-size-fits-all. There's no one-size-fits-all solution. There's no shortcuts. There's no easy way to the end here. There's not a single architecture, modulation scheme, frequency band, unique technology that's going to do it all. There's no free lunch. That's why we are pursuing a bunch of different unique optical paths across every distance to get here. Each one of these technologies that I have up here is optimized for a different design point. Each one enables a critical part of the infrastructure and addressing different requirements for density, bandwidth, and power and integration all across the stack. So if optical interconnect is the underlying technology for which next generation AI infrastructure is built, then Marvell is building the broadest portfolio with the deepest bench in the industry. But no company can deliver this transformation alone. And as Jensen talked about earlier, right, it takes an ecosystem to get here. So, like I said, technology innovation is great.